Exercise 15.1 says, for each of the following compounds, rank the highlighted bonds in terms of increasing wave number. Wave numbers are the things that are on the x-axis of an IR spectrum. So you'd have wave numbers at the bottom there. The units are per centimeter, so per centimeter. But really, wave numbers are shorthand for frequency. So how frequently the waves are hitting you. Frequencies just have really, really big numbers. For example, when you see the color blue, electric waves are hitting your eye. There are 740 trillion of them, little electric waves hitting your eye in 1 second. So 740 trillion is a really big number, so what you do is you take the frequency and you just divide by another big number, the speed of light, in a vacuum. And that gives you a smaller, more manageable, more intuitive number, which is the wave number. But notice, the speed of light is a constant, so really the wave number is going to get bigger and smaller when the frequency gets bigger and smaller. So it's a sort of shorthand for the frequency. And normally on IR spectra, if you have a spectra in front of you, on the IR spectra, you'll have around 400 wave numbers at the right and around 4,000 wave numbers on the left. So notice, the wave numbers are getting bigger as you go to the left, and that means that the frequency of the light that you're shining on molecules is getting bigger as you go to the left. So here, the waves might not hit you as frequently. Here, they would hit you really, really frequently. Okay. And so these waves of electricity, waves that hit you with this frequency, waves of light are waves of electricity. Whenever you have a charge, now you have all these different charges, and they sort of send out tendrils into the world. Negative charges reach out in every direction in the world. Positive charges reach out in every direction in the world. All of the negative charges attract all of the positive charges in the universe, and all of the positive charges attract negative charges, and all of the attractions create a sort of mesh. In physics, the technical term, the jargon term, is a field, an electric field. But it's just a sort of interwoven mesh of these electric attractions. And when you move a charge or some charged thing up and down, when you move some charged thing up and down, it creates a wave in the mesh. And that electric wave is what light is. Now, how can you make a charge move up and down? Like this charge going up and down, how can you make that happen? One of the ways you can do it is you can have a bond with a dipole, so a bond that is not completely nonpolar, and so one of the atoms will have a slight positive charge, another atom would have a slight negative charge, and the bond between them, so I'll just put a circle for an atom, because I don't want to be specific right now, but the bonds between them vibrate, sort of like a spring. Because when they're far apart from each other, the electrons on each one are attracted to the nucleus in the other atom, so that makes them come together. But then once they get together, the electrons on each repels the other one, and then they go apart. So the bonds vibrate. And when the bonds vibrate, these electric charges move up and down in that mesh, and they create waves. When they vibrate up and down. Okay, so the big takeaway from this is the more frequently that bonds vibrate, the more frequently bonds vibrate, the more frequently the waves that they make will hit you. So if the bond only vibrates slowly, then you might get a wave that's like this. But if the bond vibrates really, really fast, up and down, then you'd get waves like this. In other words, the more frequently the bond vibrates, the higher the frequency of the wave that you create, and so the higher the wave number. Now, in general, you have sort of regions on IR spectra, and you have single bonds. Those vibrate the least frequently. Double bonds vibrate more frequently. Triple bonds vibrate even more frequently. And then, even more frequently than that, are bonds to hydrogen. You can think of the reason why if you think of bonds sort of like springs. So a single bond would represent a relatively weak spring. So when you pull it apart, it doesn't force itself back together or bounce back together quite as quickly. Double bonds are stronger springs. So when you pull them apart, they bounce back together more quickly. If you pull it apart, it bounces back together more quickly, and so you get more frequent waves. Triple bonds are even stronger springs, so if you pull them apart, they bounce really quickly, and you get even stronger waves. And last but not least, hydrogens. Now, hydrogen is the lightest atom on the periodic table. And if you have a spring with really heavy weights, imagine you have like a spring here, and you have a really, really heavy weight here. If you pull on this, it's going to be hard for this spring to pull the weight back up. And so the spring will bounce in and out more slowly. On the other hand, if you put a really light weight there, it'll be easy for the spring to pull the weight back up, and so the spring will bounce more quickly. Because hydrogen is the lightest atom on the periodic table, it bounces in these bonds. The bonds to hydrogen vibrate very, very quickly. And because the bonds to hydrogen vibrate very, very quickly, they create very frequent waves. Okay, so basically what we're going to do is we're going to compare these different bonds to the scenarios in this schematic. Let me just clear this out a little bit. Okay, first, on the left side, well, maybe in the middle, you see a double bond. Of all the bonds here, it's the double bond that's furthest to the right. That would have the lowest wave number. Wave numbers get bigger as you go to the left. So that double bond would have the lowest wave number. The next higher wave number would be the triple bond. So this would be have the middle wave number. In other words, this would vibrate with a middle frequency compared to the other two highlighted bonds in green. And finally, you have the bond to hydrogen, this one right here. That would vibrate the most frequently. So it would have the highest frequency and therefore the highest wave number. And so the meaning behind all of this is that this, of the three bonds highlighted in green here, this bond would vibrate the least frequently, this bond would vibrate the next most frequently, and this bond would vibrate the most frequently. We can do a similar thing with this next problem. We're just taking this schematic and comparing the highlighted bonds to it. So here, we only have two bonds, and you'll notice the weakest one is this single bond between the carbons. Single bonds are like weak springs, so they don't bounce up and down very frequently, and they don't create very frequent waves. So that would have the lowest wave number. Remember, wave number goes hand in hand with frequency. So since that would have the lowest frequency, it would have the lowest wave number. And hydrogen, the other bond that they highlight, this one right here, that bond between carbon and hydrogen, that's going to vibrate really, really fast. That's all the way over here on the left. Because hydrogen's so light, the spring just goes up and down, up and down, up and down really fast and creates really frequent waves. Electric waves. And so that would have the highest wave number. So here you can see how these electric waves in space are related to the vibrations in bonds, and how those vibrations are sort of occur in a similar way as springs do, where stronger springs create more frequent vibrations and more frequent waves in the media around it, and lighter weights on the springs create more frequent waves, more frequent vibrations, and more frequent waves around it.